Right, well, good afternoon, everybody. This is a talk called Snowball Earth, and it's a bit of planetary science with one or two bits of astronomy thrown in along the way. But what we're going to do is look at the history of the whole of the geological time frame of the Earth to begin with. So this diagram on the right here shows the ages of the Earth that geologists carve up the whole 4.5 billion years of the Earth's history into these various sizes and different slices. Now, what you notice is that each slice is associated with a different group of fossils. So here we have the Jurassic, and here's the classic dinosaur fossils that go with that period. Okay, and the time frame here, that's 201 million to 145 million years ago, which I sometimes abbreviate in this talk to MYA. And here we are right up at the top here, newest times. If we go all the way back, you'll see that we only get to this point down near the bottom at 541 million years ago, for the beginning of this period called the Cambrian. And then there's a huge chunk here that's just labeled Proterozoic and Archean. That is actually the vast majority of the life period of the Earth, with no fossils associated with it over on the side here. So it's quite interesting that geologists have based their classification on what fossils they find in the rocks, and when they run out of fossils, they've just said, oh, there's nothing going on there, and that's actually 70% of the lifespan of the whole of the Earth. So the Earth was formed out of the material orbiting around the Sun, and all of the planets were formed out of that same whirling cloud of gas and dust that got together under gravity. It probably resulted in a whole lot of small planetoids, small planets, and then they eventually either collided and destroyed each other or collided and merged to the point where we ended up with the major planets that we have now. But those collisions would have caused enormous amounts of energy to be released, and so for the very first period of the history of the Earth, it would have been hell on earth, the Hadean era, named after Hades for that reason. They would have seen the surface of the Earth covered in molten lava for a substantial number of hundreds of millions of years, perhaps. After perhaps the 3,800 million years ago, so given that little bit of time responsible for allowing the Earth to cool down, right through to 600 million years ago, we have the Precambrian era. It's the bottom part of that first diagram, and it's a vast stretch of time. 70% of the entire history of the Earth is the Precambrian period. And again, no fossils in this period, or so they thought to begin with. Nowadays, when we study the rocks that are left, there are some fractions of rock left from this era. We do find the presence of microscopic fossils in some parts of the world. And I love this picture. I think it's very good representation of what the Precambrian era might have looked like, with enormous volcanoes and an ocean there, and then perhaps lots of hot springs on the shoreline, and one or two of those round blobby looking things that are sitting in the edge of the ocean. Those things are called stromatolites, and they are in fact mats of bacteria. The very oldest and most archaic forms of life were these single-celled bacteria, and they grow up forming these mats and lumps accumulating minerals out of the tidal areas of the ocean, and you still find them in some parts of the world today. This is a photograph taken just off the coast of Australia, where there are still these very ancient colonies of bacteria. They're still alive, but haven't changed in 3 billion years. And the whole of that Precambrian era seemed to be dominated by this and this alone. This is why we didn't find any fossils. It was all these single-celled organisms living their lives almost unchanged for 3 billion years. And so it's been dubbed Slime World, 3 billion years of slime. And then 545 million years ago, something changed. And suddenly the oceans are full of fossilized creatures, or the remains of them are there today, and the ocean would have teemed with life. These guys down at the bottom here are the early forms of trilobites, and this guy up here with the enormous jaws and eyes is called Enominocaris. And then you've got some jellyfish and other tube worms and things like that living on the ocean floor. At this stage, all life was confined to living in the ocean. But before I go on too much further, we must have a little word about how we know how old the rocks are. And the way that we do it is using radioactive isotopes. You may have heard of the term half-life, and this is where a radioactive atom or a group of radioactive atoms randomly decay into lesser, more stable atoms. And so we've illustrated that here with uranium decaying to lead. It actually decays through a number of intermediate steps, but the point is the same. So after a newly formed piece of rock has been solidified, perhaps deposited in a lava flow from a volcano, it will contain all of the elements that are normally found in whatever the rock is made of, and perhaps that might mean it carries uranium with it. But over time, randomly, each few million years, a certain number of the, or a certain proportion of the uranium atoms decay. And so you gradually get a higher and higher amount of lead compared to uranium in there. And as long as they're not getting washed out or weathered away in any other way, you can use that to work out how long it has been since the rock was formed. So that's how we do the radio dating, radioisotope dating. Now, another thing that is an important part of this puzzle that I'm going to go on to is the idea of continental drift. And I don't know if you ever looked at the BBC used to have the globe on there every time the news came on. I always looked at it and saw that South America and Africa looked like they ought to fit together. But I wasn't the first person, because in 1858, Antonio Schneider Pellegrini noticed that fit and suggested that perhaps the continents had once been joined and had drifted apart. But he didn't really have any evidence for it to start with, and it wasn't until a bit later when Alfred Wegener came along and he suggested that the continents might have moved. He also noticed that fit together and confirmed it by studying the rocks from both Africa and South America and seeing that the ordering and the sizes of the layers match perfectly. So they have been torn apart. And we were able to establish that the surface of the Earth is cut up onto all these separate plates. Some of them are ocean plates like the Pacific, others carry a continent around on top of them. And they jostle for position and move around. This is a process that we now call plate tectonics. It's responsible for the ring of fire, the volcanic activity around the Pacific there, where the Pacific plate is bashing into either the American plate or the Asiatic and Australian plates, and where the ocean plate hits the continental plates, it tends to lose. This is because it's more dense. It's actually more dense because it's saturated with water from the ocean. It would be, wouldn't it? Every little nook and cranny in the rock is filled in with water molecules, so there's no gaps. That makes it more dense. And when the two butt up against each other, the ocean crust loses and gets forced down deep into the earth and remelted, and the oceanic crust kind of floats over the top. But then the water that's carried down in that ocean crust, trapped in all the crevices, boils off due to the extreme heat in the middle of the earth and forces its way back to the surface, creating the ring of fire ash volcanoes all the way along the edge there. Now, if the ocean crust is disappearing there, then something must be being made somewhere else, because the surface area of the earth is staying the same. And that's at the mid-ocean ridges. So there's a mid-ocean ridge right down the center of the Atlantic there on the left-hand side, drawn in false color. And we're talking with the colors about the ages. So red is new and yellow not so new, green is older, and blue are the oldest rocks in the Atlantic. And they're at the edges. And again, they get crushed and subducted away at the edges, and new material gets brought up from the center. But the result of all this is that the continents move around, and it wasn't really very well understood until the 1960s that this was an important part of understanding the history of the planet. Here's a photograph that I took up in Svalbard, in Spitsbergen, north of Norway, 78 degrees north, and you can see the glacier coming down and meeting the sea there, and the amazing colors of the ice, the bluey white and the dirty material being carried along the top of the glacier, where rocks from the surrounding mountains have fallen into it. And then as it gets carried down to the sea, the ice then melts. You can see a nice little iceberg in the foreground there, but any rocky material of course gets dumped. Once the ice melts, that falls to the sea floor in those positions. And often you get great big boulders, and they're called dropstones. So a classic marker that there has been a glacier somewhere is to find these layers of silt from the glacier with occasional large boulders in them, as in the picture on the right there, a fossilized dropstone from another site. Now, the astronomical impact on all of this with the glaciation comes from a number of sources, but one of them is called the Milankovitch Cycles. Now, these have to do with the orbit of the Earth. So the orbit of the Earth is a little bit elliptical around the Sun, has a longer axis and a shorter axis, and the Earth's spin axis is tilted relative to that, and all of these possible parameters change in cycles. So the eccentricity, the ratio of A to B on the diagram there, how elliptical it is, changes back and forth with a 100,000 year period. The tilt of the whole of the orbit relative to the tilt of the orbits of the other planets changes every 41,000 years, and the wobble of the Earth's axis has two periods to it, one of 26,000 and one of 21,000 years. And so things get really quite complicated. If you plot the overall amount of energy that is received by the Earth, because it's all coming from the Sun, so if the distance from the Earth or the angle of tilt away from the Sun of the polar regions changes, then the amount of energy received at the northern and southern most extremes during the different seasons changes. And that can be plotted here. This is for 65 degrees north, so northern Norway. And you can see how over thousands of years, the power received from the Sun wobbles about according to the sum of the effects of all of those cycles. And so sometimes it's receiving perhaps only 440 watts per square metre, other times it's 540 watts per square metre. And that's going to make a big difference to its tendency to retain ice. So the glaciers tend to advance and retreat according to the beat of this particular pattern. Now, this is where the story starts to get really interesting indeed. This is a photograph taken by a scientist called Paul Hoffman, who's the real star of this story. And it's a dropstone. You can see the layers of silt there and the large boulder that's thumped into them and made a dent and then been fossilized in position and exposed. And there's a coin for scale there. And this is in layers of sediment that are dated by radiological dating to 600 million years ago. So just before that Cambrian period where all the fossilized life suddenly appeared. Now, above and below these layers where we found the dropstone, there are layers of carbonate rocks that suggest that they were formed in shallow seas with a warm temperature. But this rock formation is in Namibia, southwest Africa. And Namibia today is a hot, dry desert. And the last thing you would expect to find there is a glacier. So one explanation is, well, perhaps the continents have moved and maybe Namibia was somewhere colder 600 million years ago. But Paul Hoffman decided to investigate this a bit more thoroughly. And he took samples from the same period all around the world, 600 million year old rocks, and he kept finding more dropstones. Here's one from Canada, large boulders pushing down on those rusty banded formations, both above and below the layer of glacial dropstones. Now, surely not all the continents could have been at the pole at the same time. They just wouldn't fit. You can't have every continent on Earth being a polar continent. There's just not enough room at the poles. So that's a bit suspicious. But fortunately, you're able to get a handle on this because of the Earth's magnetic field. When rocks are laid down, they trap and remember the Earth's magnetism. And in particular, they trap the direction and the angle of the field lines. You can see on the right there, the Earth looks like it's got a bar magnet through it, and you can see the field lines going from north to south and back. And if you're at the poles, then the field lines meet the ground nearly vertically. But as you move further south, you can see that the field lines down at the equator are going almost parallel horizontally to the ground. That's called the dip angle. And if you measure the dip angle that's in the fossilized magnetic field in your rocks, you can work out the latitude at which they were formed. They might have moved after they were formed, but that is the latitude they were formed at. Because when they're liquid, they don't trap the magnetic field. When they solidify as they're being formed, they trap the field there and then. And by doing that, he discovered that his rocks in Namibia told him that the field was horizontal and that the 600 million year old glacier was therefore formed at the equator. And nobody believed him. Now, there's another picture I took when I went up to Svalbard, and here we've got some layered rocks, sedimentary rocks, laid out in layers. You can clearly see them running horizontally. And down at the bottom, just above the waterline there, we've got a layer of reddish coloured boulder clays. These are indicative, again, of glaciers, of ice on the move. Well, this is Svalbard, 78 North. No one should be surprised. But again, these are ancient Precambrian rocks. and you can show by looking at the magnetic field that at the time Svalbard was in the tropics, and above them and below them there are carbonates that again form in warm waters. And we know that Svalbard was making its way north all for the last 600 million years ago. It's moved up along and to reach its current position by studying this magnetic dip in the different layers. So all of this is pointing to the fact that it didn't matter where you were on Earth, there was a global ice age, the Snowball Earth. The Earth perhaps would have looked something like this, completely covered in a layer of ice many kilometers thick. And one reason for this was worked out when they were first doing some of the computer climate models to try and understand the behavior of the Earth's atmosphere and its climate. And what they realized was that ice reflects the light much better and the heat much better back out into space than either land or ocean. And so as the ice grows during an ice age, it actually causes an acceleration in its own rate of growth because it makes the planet more reflective overall. And so it accelerates away from the first beginnings of an ice age. And they calculated that once it reached the tropics, where most of the heat of the sun is landing, it would reflect it away and run away. It'd be a runaway process and create a full snowball. But then, in a double whammy, the extreme cold of that snowball Earth would be about minus 40 degrees centigrade. And so all the water vapor in the atmosphere would freeze out onto the surface, adding to the ice and drying the atmosphere. But water is a very powerful greenhouse gas and heat helps keep the temperature of the planet warm for us at the moment. Without it, we'd be at minus 20 or so most of the time. But with it frozen onto the surface at minus 40, it's going to make it even more likely to stay cold because you're letting even more of the heat get back out to space. And so this locks the whole planet in. No escape from the snowball. Well, there must have been, because we don't see this today. So how did it get away? How did it break out of this? And the answer turns out to be volcanoes. All of that heat of formation of the Earth from the impacts during the Hadean period created a planet with a solid crust eventually, but still with a very hot molten interior, and all of that heat is still bursting out through volcanic eruptions, and it brings with it into the atmosphere lots of gases, carbon dioxide being one of the most important ones. And so while you have the snowball Earth, the volcanoes are still delivering carbon dioxide into the atmosphere. But normally, carbon dioxide flows in a cycle. What happens is that the carbon dioxide dissolves in the water vapor in the atmosphere and rains out as dilute carbonic acid onto the mountains and the hills. Then it reacts with the rock, with the silicates in the rock, and dissolves them and flows down in dissolved solution in the rivers into the oceans, and then precipitates out as carbon in calcium carbonate onto this ocean floor. And then of course the ocean floor eventually gets subducted back down underneath the continents again, only for the carbon dioxide to be re-released by heating to come back up through the next volcano. And that process of going right round that loop takes about 200 million years for carbon dioxide to go right round that recycling process that's happening all the time. Except when you have a snowball Earth situation, all of the rock is prevented from reacting with the carbon dioxide because it's covered in ice. It's not accessible to the carbon dioxide in the air. And there's no water in the air either, because that's all frozen out, hard as iron in ice. And so the carbon dioxide doesn't form into acid rain. And if it did, it wouldn't actually manage to get to the rocks and react with them. So the cycle is broken and carbon dioxide just builds up and up and up in the atmosphere. We have about 440 parts per million of carbon dioxide in the atmosphere at the moment. We've managed to quadruple that in the last 100 years from 100 parts per million. But during the Snowball Earth, it got to 7,500 parts per million, which is vastly greater. So the greenhouse effect was building up. And of course, that is what warmed the planet back up, eventually melting the ice. Another curious feature of the geology around that time is these banded iron deposits. Now, if we go right back to 2,000 million years ago, 2 giga years ago, 2 GYA, life was just inventing photosynthesis and pouring oxygen into the atmosphere. And all the iron that had until then been dissolved in the oceans, having been brought up from the deep earth by vents, suddenly found itself being oxidized and deposited as well as what is essentially rust. They're hematite layers that you can see in this rock, and you can see it went in waves. You have iron being deposited and then other minerals, but a vast amount of iron was deposited out in these huge banded iron formations caused by life changing the atmosphere. Well, that's a long time ago. That was 2,000 million years ago. We're talking about the curiosity of this glaciation of 600 million years ago. But we found the same thing, these banded iron formations occurring in that Precambrian period around 600 million years ago. More evidence of these iron accumulations happening again. Now that's very curious because somehow that meant iron had reaccumulated in the ocean and then got itself dumped. Now, under the snowball conditions, of course, the undersea vents were still pushing metals and metal salts into the deep ocean. But again, the ice layer is acting as a barrier to the atmosphere. And so the oxygen in the atmosphere is not able to rust this iron and cause it to precipitate out. So it would build up and up and up to a very high concentration until those volcanoes have caused the carbon dioxide to reach these enormous levels. As I said, over 1,000 times today's level was reached, and create a massive greenhouse effect that would bring the temperatures up and melt the ice, cracking the snowball's grip. And immediately then, when that happened, the oxygen in the atmosphere is able to get at the iron in the water again and precipitate these layers out. So the whole story starts to fit together and explain some very curious features. Now, what happens then is, of course, you get vast overshoot, and the carbon dioxide in the atmosphere has caused this huge greenhouse effect. And so vast amounts of water are now evaporated back up into the atmosphere, and that adds to the greenhouse, causing a potential runaway to the hot extremes, and the temperature soars back up from -40 to +40 in very short order. This is quite a climate catastrophe, really. Eventually, the exposure of the rocks to that enormous acid rain storms that would have happened with all that carbon dioxide and water raining back onto the now exposed rock on the land brings things back to balance. The carbon dioxide is sucked back out of the atmosphere, back into the oceans and precipitated. And so you end up back with a fairly normal planet again. It's quite a wild ride though for a while. But it begs the question, what triggered it off in the first place? Was it just the Milankovitch cycles causing an ice age? Well, actually, the Continental Drift was partly responsible as well. Before all this happened, about 750 million years ago, all of the major continents that we have got together to form a supercontinent that we now call Rodina, the motherland. And it was mostly at the tropics. Now, it makes a difference to the climate of the Earth where the continents are, because most of the heat arrives at the tropics. The low angle of attack of the sunlight coming into the polar regions is why they're colder. But the land and the ocean also affect this because they absorb the heat differently. If you have land at the pole, then the land can potentially become ice covered, and that stops it pulling carbon dioxide from the atmosphere and increases the greenhouse warming. So land at the poles tends to make for a warmer climate and slow the advance of any ice. So that makes for a bit of negative feedback. If the land at the poles is covered in ice, then you get more greenhouse gases building up in the atmosphere, and that tends to make the ice retreat again. But if you have land at the equator, the land reflects more heat to space. The ocean is very good at absorbing it. So if you have ocean at the equator, you absorb heat. If you have land at the equator, you tend to reflect it. So land at the equator tends to make a colder climate. And if, as the ice is advancing from the poles, it's doing so over the ocean, not over the land masses, then there's no reduction in weathering and no reduction in carbon dioxide being pulled out of the atmosphere. And so no increased greenhouse effect to slow the advance of the ice. And so when you have land at the equator and not at the poles, the ice can advance a lot further, and it can reach that critical tipping point where enough of the surface of the Earth is now ice covered for it to do the runaway to completion. And all this led to snowball cycling. The period 750 million to 590 million years ago, there were actually 3 occurrences of these snowball periods interspersed with the enormous hothouse conditions of a runaway greenhouse effect. So each snowball leads to carbon dioxide induced retreat and a hothouse, and then it goes back the other way, returns to normal. You can see it in this diagram, and we've got a plot of the surface temperature, which we can also work out. So you can see from the bottom there, at 750 million years ago, things suddenly took a turn for the colder side, and then it went into the snowball episodes and eventually broke back out of it and returned to normal. All it was waiting for was a nudge from those Milankovitch orbital cycles to tip it into the snowball, and it's all due to the position of the continents being at the equator. But the final escape from this snowballing is when the large supercontinent Rodina broke up. So it formed at the top there 825 million years ago. in the north polar regions, migrated southwards to the equator 750 million years ago and began that snowball cycling period. But as it moved further south, it started to break up. And by the time we got to 530 million years ago, there was enough land now at the polar regions to stop the runaway snowball effect. We've also been able to trace a previous occurrence of this happening, and that was way back, even before those little blue-green algae had got to work on the atmosphere and invented photosynthesis. This is 2,400 million years ago, deep in the Precambrian. Again, there are evidence in some parts of the world of dropstones and these overlying carbonates, which are the signature of a snowball Earth. And again, it turns out there was another coming together of most of the major continents. India was up there at the North Pole, but all of the rest of them got together in a supercontinent at the equator, which has been given the name Kenor Land. So we're pretty sure that these snowball events happen, and when they happen, they last for 10 million years or so before the volcanoes break things back out again. So how did life survive any of this? With the whole surface of the planet covered in ice, you should think that it would shut off any access to light and photosynthesis. So all of those blue-green algae would be in real trouble because that's their source of energy. And so there would be some sort of mass dieback. But perhaps there were some thin regions of ice. Perhaps there were some small areas of land that were exposed that have still been pretty cold, perhaps. But again, I think it's volcanoes that saved the day. This is a picture of some hot springs up in Iceland, and lots of blue-green algae and all sorts of interesting biological specimens growing in the hot spring water. And these few pockets would have perhaps remained ice-free and warm enough for life to cling on just in these few pockets of geothermal activity around about the surface. But it will also have been able to cling on in the deep ocean, where hot water and superheated steam and minerals come pouring out of the ocean floor in what we call black smokers. You get a lot of organisms there that live on the chemistry of the material that's coming out. They don't depend on the light of the sun, and this may well have been where life first got going on the Earth. All the evidence of the very first instances of living creatures points to them having evolved at these black smokers on the ocean floor. And any such life down there wouldn't even have noticed that the entire surface of the Earth was now covered in ice. Now this is where Paul Hoffman had the light bulb moment. Perhaps he thought this global ice age, this snowball Earth, was the trigger that broke life away from its complacent state of slime world, where nothing had really changed for 3 billion years. Perhaps it led to the explosion of the number of species and the complexity of life. Suddenly life would have been presented with a near clean sheet once that ice went away. And the diagram on the right here is just the period from the snowball going forwards, showing the numbers of species on a sort of upward trend. And then there are a number of little yellow circles with numbers in. Those are the big 5 or 6 mass extinction events. Number 1, number 2, number 3 there, number 4, and number 5. Number 5 is the event where the dinosaurs died out 65 million years ago between the K and the T. That's often called the KT boundary event. Number 1 is the end Ordovician. We can talk more about that another time. And then the Great Dying, number 3 there, the end Permian event, was a very substantial drop in the number of species. But before 0 there were almost none. Almost all the complex species on Earth suddenly appeared at the end of this snowball period. And so suddenly, as we saw, the oceans were teeming with life like this. And that's a big jump to make, to go from slime worlds to this, almost overnight. Well, that's not quite what happened, as it turns out. Future research has shown that life was heading towards complexity even before the beginning of the Cambrian period. We can squeeze back from 545 to 555 million years ago with this Dickinsonia fossil that was found in Australia. And that's pushed it back about 10 million years. Newfoundland, we can go back a bit further, another 10 million years with the mistaken point fossils. Another 10 million a little bit further up the coast to 575. And we date all of these looking at the DNA. We actually managed to recover samples of DNA from all of these fossils, and you can figure out how the tree of life has evolved by looking at the number of mutations in the DNA. Here's an example of how it's changed over time with different plant species around about in the last 300 million years. And we can figure out what evolved from what by looking at how many mutations have occurred in that molecular clock. So you can piece the whole history of life together and in fact trace it back before the Cambrian and discover that maybe another 500 million years before that, the single-celled creatures were just beginning to get together and form multicellular ones. It was then, once they got the trick of multicellularism, that enabled all of the rest of the complexity to form. Here's another chart that shows the history of life, again, all the way back to 4,600 million years ago. And it seems that life has had quite a bumpy ride over all of that time. And it's those bumps that give life a nudge, because it shakes it out of its complacency and makes it move on. Now, another astronomical impact on all of this, of course, is the sun. And the sun has been getting hotter ever since it was formed. There's a diagram here showing how the radius of the sun, in fact, is increasing. This is as it's gradually turning hydrogen to helium in the core, it's slowly swelling up. And the temperature of the surface staying about the same at the moment, but the output, the total power output, is the red line. So you can see that it was quite a lot cooler in the past being on Earth than it is now, because of the power output of the sun has been increasing and is going to carry on increasing, and will see the end of all life on Earth in about 1 billion years' time, due to the fact that it's going to become a red giant. So at the moment, we live nicely in the habitable zone. Mercury and Venus are too toasty warm, and Mars is just on the outer edge of that. But of course, that chart shows that the sun is gradually putting out more heat, and so we are going to get warmer and warmer, and likewise Mars is going to warm up. Well, that'll probably be good for Mars because the temperature there is a pretty chilly -5 on a good day to -87 on a not so good day, and all of the water that's left is frozen solid into the permafrost. So maybe warming that up will mean that we might one day have to abandon living on the Earth and take a step outwards to the fourth rock from the sun. Eventually, the sun is going to start really swelling up, and that habitable zone is going to sweep outwards past Mars and leave it behind, and out to the outer planets being at a sensible life-supporting temperature. Now, I wouldn't think we would ever go and live on Jupiter or Saturn, but those are not the only bodies out there. There's 3 snowball worlds of the outer solar system. We've got Ceres in the asteroid belt, Europa, moon of Jupiter, and Ganymede there, also moon of Jupiter. So the first phase of the warming might be to melt the ice on these worlds and maybe end their snowball lock-ins. Maybe that will be the trigger for any life that's trapped underneath the ice, and maybe that's what's responsible for this red coloration coming up through the cracks on Europa. Maybe that will release the brakes and cause a period of rapid explosive evolution on these worlds, if of course there's any life there at all, which at the moment we just don't know. Out at Saturn, the very interesting little world Titan there that's imaged by Cassini might well get warmed up to the point of being able to break free of being locked in rather a deep freeze. And Enceladus at Titan as well, at Saturn as well. There's plumes of material coming out through the tiger stripes, and those are carrying with them organic materials and hydrogen, and that's exactly the signature that you expect from the chemistry of iron sulfur living bacteria living at the boundary between the rocky core and the under the ice ocean. The chemistry of that says that iron sulfide reacts with water, and one of the outputs of that is molecular hydrogen, and that is something which iron-loving bacteria produce on Earth at the moment. So maybe that's what's going on deep in the core of Enceladus, and maybe once the sun warms up and the ice here melts, this will no longer be a snowball world either. There are 2 more moons of Saturn, Rhea and Dione, that are in this state, and even out at Uranus we have Oberon and Ariel here, 2 moons there that are snowball worlds that covered in ice. Who knows what's going on underneath? Of course, right out at the outer reaches, we have Triton and Pluto here. Triton, moon of Neptune, both showing interesting chemistry on their surface. I wonder what will happen to them when they get warmed up. Now, the bad news is that you'll only have 500 million years while the sun is in its red giant state, not the 10 billion that the inner planets have had by that point. But 500 million years was enough to go from the Precambrian single-celled organisms to produce all the complexity of life that we see around us. That's when all the interesting stuff has happened. So who knows what's going to happen in the outer parts of the solar system while the sun is being a red giant. Of course, you're likely to come to a sticky end when it finally dies shortly afterwards, but it might be a good 500 million year run. And again, we think that the black smokers that are probably happening on all of those ice worlds at the rock water boundary underneath them is where life got going on Earth. So why not on all of these snowy worlds out there? And so that's it. It's the end of the talk I put together about the Snowball Earth.